Today I'd like to talk about measuring low-level currents. The type of thing you might see in an IoT application where you have a low-level sleep current switching up to perhaps a relatively high-level current when the device switches into transmit mode. So what we've done to simulate it, I have an arbitrary function generator built into this MDO 3000. So I've literally drawn a waveform that would be kind of representative of the power profile for an IoT device. Let me show you the waveform settings. What I've done, I've put a 25 millivolt low level, so corresponding to our sleep current here, I have 25 millivolts. Then stepping up, perhaps as the processor woke up, started processing, maybe turned on its sensors, gathered some data, switched through to transmit mode is our high peak, and then switching back down to a relatively low level as it tidies up and then goes back into sleep mode. So that would be kind of representative of a typical IoT device. I've taken the output of our AFG, looped it through a couple of cables through our DMM here just to measure current onto a 50 ohm load. So obviously simple Ohm's law, I know if I'm outputting 1 volt peak into a 50 ohm load, that's 20 milliamps flowing through this cable at that peak point in time. So if we want to make a simple current measurement, get our mean current to see how long our battery is going to last, I can put it on a simple DMM like this. That's showing approximately half a milliamp as its kind of ballpark reading. That would correspond to our low level sleep current, but on the maximum it's showing 1 milliamp, and that's simply because a standard conventional bench DMM, regardless of who it's from, this one's Roden Schwartz, it could be a Tektronix, Pico, anyone at all, a normal DMM is not designed to measure fast signals like this. You know, if you look at the scope, we're on 100 microsecond per division, that's roughly what, 30-40 microseconds I've set for that transmit duration. A normal DMM simply isn't fast enough to measure it. So we can rule this out as our instrument of choice. If we want to measure our current profile, we could use a current probe. So I also have one of those set up. Here I have a TTI iProber, positional current probe. This is a slightly odd probe in that it can measure current in a PCB trace. So if we were to remove this, you would literally hold that on top of a PCB trace and it can measure the current in the trace. But it comes with this little adapter, lets you use it like a conventional current probe. So we just clip that on there around our wire. We're now picking up the current that's flowing in that cable. Let's pop that back down. Okay, so I have that set up on channel 4, and we've got a noisy waveform here. First, I should probably point out, if I turn off the AFG output, okay, we now know there is zero signal or zero current there, and yet we're still a lot of noise and we're about the zero line. For a current probe like this, the first step is to actually null out that zero, so you need to set it to 0 as best you can, and then we can make a sensible measurement. So we'll turn our AFG back on, or scale up. Okay. So as you can see, we've got a very noisy waveform. It is giving us our 20 milliamp peak to peak. I'm on a 5 milliamp scale here. The probe itself is 1 milliamp per millivolt. So we're on a fairly low level setting on the scope, so we're seeing the noise. I've optimized this as best we can. I've set the bandwidth limit on the scope to 20 meg. I've set the bandwidth limit on the probe to 500 kilohertz. And yet we still have noise. So I can cheat and turn on the averaging. Obviously, because I'm using a repetitive signal coming off our AFG, we can average that and get a sensible measurement. I'll just adjust my 0 a little bit there, bring that right up. Whoops. Yeah, as you can see, it's a very sensitive adjustment. But okay, so there's something kind of representative of what we're trying to measure. But of course in real life we can't be sure of a completely repetitive signal, so we can't use average. The alternative approach is we need a more sensitive probe. So 1 volt per amp is kind of typical for your lowest sensitivities on a current probe. So to get higher sensitivity, we cheat. I'll just show that now. Obviously, if we've got one cable flowing through here with 20 milliamps, if I loop that around and float it through again, put a 40 milliamps, again, it'll add up. So I should be able to get a few loops around this. Pop that out a second. Hopefully you can still see what I'm doing here. So I'm literally just going to loop this around. Now, 2 turns, 3, 4, 5. So our probe is now 5 times more sensitive. The drawback, of course, back to front. The downside to this trick is we've increased the insertion loss, but for this low frequency stuff, it really doesn't matter. So pop that back down there, plug that in. Okay, you can see we've got a much bigger waveform. Pop this down. Okay. Adjustment 0. So that's given us a current measurement we can actually make use of. We're still in sample mode, we're not averaging. I'll just prove it. I'll turn on the averaging. Obviously we've got a perfectly clean waveform, but we can't trust average because our signal may not be completely repetitive. So there we go, we can now measure our 20 milliamp peak, our low level kind of half a milliamp, background. Yeah, it's usable. We do suffer a little from the offset of the probe, where you couldn't really trust it to make an accurate measure of this sleep current, but you could use that a normal DMM to measure that and get your current profile off that. Not ideal, but it's doing a better job than our DMM did. The one big drawback with this is we don't really have the dynamic range. On this this scale, here's 20 milliamps. Here we're down in the noise. It'd be very difficult to make an accurate measurement of that, but it does work. There is, however, a better tool for the job, and if you bear with me, I'll just swap out this DMM for an alternative. Okay, so what we've got now is a Keithley DMM 7510. See it? This is still a digital multimeter. Does all the things a DMM would do. However, it's much faster. This unit will measure at 1 megasample per second. So that's going to give us the resolution we need in the time domain. We can get our 1 microsecond resolution. Good enough for what we're after. Just see my current waveform has drifted off there. Pop that back down. Okay. Now, I've already preset this, so I'm just going to cheat and go ahead and do it. I'll clear my buffer, trigger. Okay. Now we can see our maximum 19.91 milliamps. Our minimum way down 0.22 milliamps, and our average is giving us 622.55 microamps. Okay, so that's obviously making an accurate measurement of, because we know what we're expecting here. We can actually do better than that though. If we go in and have a look at the graphs, that's I've set this for I think 10k points. So it's captured a number of iterations of our signal, and it's a touchscreen interface. I'll try and zoom in on one of these, let you have a proper look at it. Okay. Okay. So as you can see, we have an actual waveform displayed on our DMM. So if our multimeter is behaving more like an oscilloscope, and yet we have the resolution. You can see there's no noise on that. We can get our low level of our half a milliamp, we can get our 20 milliamp peak, we can see the exact profile of it, and more importantly we can do that over an extended period of time. Our oscilloscope is going to be limited in what we can capture in the time domain. You know, if I bring our time base away down, yeah, I can capture a few cycles. So, you know, it's going to start running out of sampling speed, so, and obviously I couldn't capture hours or days worth of information. With the Impact 10 we can still capture high rate, capture our full profile, very low noise floor. Yeah, it's the right tool for the job. Let's see, we can actually set it to trigger falling edge, so that's just how I've got it set up. And we can capture, you know, a single waveform. We can do repetitive measurements on it. We can take multiple iterations, just trigger it, we'll do another measurement, 19, or I can leave it running, doing continuous measurements. So you see it's gathering up lots and lots of readings here. That's all I want to show you. The right tools for the job, I think, is the key takeaway for that. A normal DMM is just too slow. The oscilloscope will give you a certain amount of information. There are limitations when you're trying to measure these very low currents. If you'd like any further info, you can check this out on our website, or of course feel free to contact us. Thanks a lot.